Welcome back. Can you speak now?
We're still not hearing you if you are speaking.
Can you hear me now?
Yes.
Thank goodness. Okay. So I hooked up the speaker, but evidently I did it before Zoom was in, so it didn't know what to do. Anyways, I think that's decent. Sorry about that delay and confusion and all that good stuff. Hopefully y'all can hear me, hopefully even better than normal, since I'm using a mic. So before we start, does anybody have any questions about anything? Hopefully everybody noticed I did put the test up. I also put up, I think I put the practice test for next time up as well, for the next test. In other words, chapters 25 and 26. So y'all should go ahead and start doing that now that once you start doing chapter 25, you should go ahead and start playing with the practice test a little bit. And that's what we're covering today is 25. I probably, well, depending on time, I might be able to cover it all right now. I at least can cover enough where y'all can do all the homework. So I guess we'll go ahead and get cracking on that. So we're starting off with basically chapter 25, which is called electric currents and resistance. And it's really just some fundamental things you got to know. And I suspect if y'all have done anything with electricity, you know most of this. But Alessandra Volta is the person credited with creating the first battery. And he actually discovered it by looking at frogs and realized little twitches in their leg muscles, even though they were dead. These are, frog parts, not frogs, cause their muscles to twitch. Ultimately, what we know now is that basically if you have two dissimilar metals, so if you have copper and zinc or anything like that, and you put them in an ionic type solution, what we call an electrolytic solution, Gatorade, for instance, it has some ability to be electrolyte. It's not as good as you might think, because it's good for humans to keep their electrolytes, but it's not as good as you might think. But to give you some idea, for instance, all you have to do is you can take a copper wire and jab it in one end of an onion or a apple or a lemon or a potato, and then take a galvanized nail. Galvanized means it's usually covered in zinc and some other metals, and jab that in the other side. And then you put a voltmeter across it, and it'll read on the order of probably 0.5, 0.7 volts, something like that. Now, if you put another one next to it, the same way set up, only this time you have the copper nail, or the nail connected to the other copper wire on the other lemon, and then read across that, you'll get twice as much voltage. And if you keep doing that, you can get enough voltage to do something significant. And each of those are more or less considered an electric cell. One way you can do it, and this explains the symbol that we use for a battery, which is basically a long line followed by a short line right below it. Sometimes they'll have 4 of them, so it'll be a long, short, and the short side's the low voltage side, usually recognizes 0 volts, and the long side is the high voltage side, the plus side of the battery, the 9-volt battery, the AA, the AAA. And in fact, all those higher voltage batteries that we deal with, like I have a 12-volt battery that recharges itself in a cross trainer, elliptical cross trainer I have, and it was kind of neat. My ex-wife gave it to me, told me she wasn't using it anymore, I could use it. So, it's been really nice sitting over there in the office with clothes hanging on it. I don't want to touch it or anything, but the battery was dead. And I opened up the battery, and it was nothing but a bunch of D batteries inside of this one big battery, all wired together. So that's the way batteries are made. They're all just made out of small little cells. They just add them together. So that's kind of interesting. But one of the ways you can make them is you can take, for instance, a pill bottle, and you can affix a wire, say, to a penny, solder it to the penny or something like that, drop the penny in the bottom where it lies flat in the bottom of the pill bottle. Then take a little gauze maybe and stick on top of that. So a little piece of paper, piece of cotton gauze or whatever, stick on top of that. And then take a little piece of, let's say, a nickel would be fine, for instance, and stick that on top of it, and then stick another piece of gauze, and then another penny, and then another piece of gauze, and another nickel, and keep doing that as many times as you want until you get a nickel on top that you're happy with. Okay, because the more of those you stack up, the more voltage you'll get. Now you just backfill it with some liquid, like it could be apple juice, or it could be sulfuric acid or hydrochloric acid. Be careful with those. They will actually eat the metals, but that is in principle what could be done. But literally, you can just say salty water solution, that would work fine too. And if you connect the wire that was attached to the penny and then attach another wire to the top nickel and compare those, you'll have a pretty good voltage out of that. And that is essentially what a battery is. Now they've gotten it real smart. Now they use, as a conductor, they use carbon. So you'll literally see if you opened up a battery, which they tell you not to do, which is of course the first thing I did when I learned that you're not supposed to do it. But if you open it up, you'll see it's just a black pasty stuff with metals on the inside and touch the bottom and stuff like that. And in fact, that stuff that pasty stuff could burn you. So don't mess around with it, and it could explode when you're messing with it because it's flammable. So there's a lot of good reasons to heed their advice. I'm just not one of those people that do that. Someone tells me don't pee in a light socket, I pee in a light socket, and I literally did. So yeah, it was probably, I'd like to say it was 3rd grade, but I think it was like 5th or 6th. And I'm in the bathroom and at my old Christian school, and my friend David Folk walks in, and I'm sitting here, I'm looking at the urinal, I'm looking at him, I'm looking at the electrical socket. I said, "Hey, David, I dare you to pee in that socket." He's like, nah, man, I ain't doing that. I was like, well, shit, I'm curious about it now. I want to do it. So I walked up to the light
As
socket.
long as it wasn't last year.
That was a bad day. I was like, I saw a little blue flame fly up into me. Oh, it was horrible. Funny that school still exists. In fact, that's the place where my mom and dad got married, is at the church's Bethany Christian School in Portsmouth, which is now just a church. It's Bethany Christian in Portsmouth on Portsmouth Boulevard. And my cousin got married there a decade or so ago, and I went there, and that bathroom socket's still out. They got it all plugged up. I'm like, the managers or the maintenance guy probably like, "It smells like urine and it ain't working. I don't know why. I'm just gonna close that thing. That's weird." So yes, I am that guy that tries stupid stuff. So I'm actually kind of proud of it, though. It's the experimentalist in me. I've done numerous things like that. My daughter, she makes me proud. She walked into a pet supply store one time and saw a salt lick, and of course I looked at her and her face was all, I was like, "You licked it, didn't you?" "Yep, she did." So that's the experimentalist, the scientist in us, I guess. I don't recommend living my life. I just think it's funny, and maybe my students will get some enjoyment out of my losses. So now that I've discussed basically what a battery is, once we had a battery, we could actually study electricity, because before then it was like you were just trying to make electricity by cogs, and you'd rotate a Wilmhurst wheel or something weird like that, or you use what they call condensers, which are modern day capacitors, where you'd store up charge on it and then release it all at once, but you really had no control of it. Once we had a battery, we could actually suspend or cause the voltage to go through for a long period of time. And that allowed us to study things, and we were able to come up with, for instance, Ohm's law, which you guys have seen in lab. So your book takes some time to explain that. It talks about Alessandra Volta, and they call them piles, which is kind of weird, but you'll notice that that's also what they called the nuclear reactor that Enrico Fermi built at University of Chicago. That's why it's basically any source of energy originally was this pile. So a lot of things have been called piles since then. And sometimes there actually are piles of stuff that are connected together in a pile type fashion to make power, or to make energy in this case. So your book takes time to show you basically what batteries are. So you typically have like a AA or a AAA battery, and the little nipple on top is the positive end, and the little dent on the bottom is the negative end. And if you wanted to make twice as much voltage, because nominally a AA, a AAA, C or a D battery, they're all supposed to be 1.5 volts. In fact, if you put them on a voltmeter, they'll read like 1.73 or something like that. And that's because over time they're going to get weaker and weaker. And when you draw current from it, that voltage difference gets smaller and smaller as well. But if you wanted, instead of 1.5 volts, you wanted 3 volts, well, you just stack two on top of each other with the nipple up against the negative, bottom, and then the nipple up here and the bottom down here. Now you got 6 volts, or excuse me, 3 volts. And then another one that would give you what, 4.5 volts. And then another one would give you 6 volts. So you can just keep adding them up like that, or you could actually wire them beside each other. Little caution with that, because you get a battery really hot, bad things can happen. But a lot of people will actually solder the wire to the battery, and that works if you know what you're doing. But if you're using too high a temperature, it could be dangerous. The other thing you might want to know is how do you hook up a light bulb? Well, if you want to run a light bulb, like an itty bitty little bulb like that, with a battery, all you need to do is take either the positive side or negative side and touch it to the threads on the light bulb. So you got that gold metal thread around the outside of a light bulb. Well, on the bottom, you'll look, and there's like a little black plastic thing, and then there's a little nipple that sticks down, and that's usually like a different metal. In fact, it's usually lead. You can lick it to see if it's sweet, and that's another dangerous thing, but that's really what one way you used to tell lead was that it was sweet. But the neat thing is you can take the positive side, say, and stick it to the gold threads, and then you take the negative side and stick it to that lead, or you could even melt that lead or solder it to that. And that's partly what that is. That lead is there so you can solder it to the light bulb if you wanted. So if you actually put a soldering iron on it, that metal will come liquid really quickly, and you can attach it to it. But that's neat, because a lot of people don't understand that. That's really how the socket works. It's got the threads is one terminal, and the little button on the bottom is the other terminal. So that's sort of some neat stuff that you should keep in mind. The other thing that you need to keep in mind is that really you can sort of imagine batteries as if they're sources of positive charges flowing out the positive end. And in theory, you always want those charges to come back to the battery, even though generally speaking, you're not really taking charges out of the battery. You're just compelling the charges that are free in the conductive wire to move around in that way. But in reality, it's actually negative charges that are moving the opposite way. But we do something called conventional current. Basically, Ben Franklin had 50% chance of getting it right. And he guessed the thing that we call positive were the things that were running around. Turned out it's the things that were negative that were running around. They're running around the other way. But we had invented so much about electricity by then, we just kept the terminology, and we called it conventional current, which suggests that the positive charges are flowing away from the positive voltage towards the negative voltage, when in fact we know it's actual electrons that are able to come loose from the atom, and the electrons are of course negatively charged. So it's the negative charges moving around that really complete the circuit. But the main part you're supposed to get from that is the circuit should be closed. In other words, it should be coming from the positive source of voltage, and then attaching to some load like a resistor or a battery or an air conditioner or something like that, and then from that return back to the battery. So you should have that sort of closed circuit. There are ways you don't have to do that. For instance, if you've ever seen somebody jump a car, sometimes they don't connect both terminals. They'll connect the black, say, for instance, to the frame of the car. Oddly enough, that actually does work. And a guy by the name of Oliver Heaviside wrote a paper back in the 1880s, I think, 1880s, 1890s, where he talked about using the ground as a return source. So literally you could run voltage out in principle and then take that at the end after it goes through the load and just stick it right in the ground. And in fact, that ground that you look like when you look at a light receptacle has a little slit, and then it has a taller slit, and then it's got a little mouth under it. And it's usually mounted that way where the slits are here and here, and then the mouth is there. A more conscientious, but less, and maybe even more OCD electrician will wire it the other way, because when you have it the way that you traditionally do, then the two wires on top, those are the ones that can bite the crap out of you. So you can imagine if the receptacle pulls out or the plug pulls out of the receptacle a little bit, and you're a kid walking by with, say, a nice metal ruler, first thing you're thinking is, pow, and it pops you really good. So it's best that those top ones not necessarily be the two, because one of those is the hot wire and the other one's just neutral. So you turn it upside down. Then if the child drops or hits something on top as it comes loose, then they'll hit the ground one. But that ground one, that little mouth, that's all those are attached together basically. They get back to the circuit panel, and then there's one mother of all wires that sort of runs out of the circuit panel and goes literally to a little vice clip, if you will, a little clamp that's attached to a 8-foot long solid copper pole. And you take that 8-foot long solid copper pole and you stick it on the ground and you bang it in all the way till it's completely submerged, and that's your ground. So really, when you run anything to ground, that's exactly where the charges are going. So that's something to keep in mind. But generally speaking, we just make our circuits complete loops. We don't, leave them hanging. So that's something you want to think about, and how to connect batteries. That's why they showed you on figure 25.7 a bunch of different ways you can connect a battery to a light bulb, and like they're wrong. Only one of them's right. So make sure you know how to do that. That's me trying to give you the practical side. Now, what's really going on, as I told you, is the battery isn't necessarily sending charges out, but it's really ultimately establishing an electric field throughout the wire, and the wire is acting like a little waveguide that makes it vary along the wire. And because that has an electric field, that's going to compel loose charges to, if they're positive, to flow in the direction of the electric field. If they're negative, they're going to choose to flow in the opposite direction. But again, we're always going to pretend like they're positive charges. And there's really only one experiment you can do. It's called the Hall effect, to show that they're going the other way. So it's not really a problem to picture it that way. So that's we've talked a little bit about voltage. I already told you that voltage is basically the energy per coulomb. It's joules per coulomb is what a volt is. So you can think of voltage as like a potential energy, because it literally is an energy per coulomb that you apply to it. So for instance, if you take something 12 volts and you put 1 coulomb on it, it's going to have basically 12 joules of energy. And that 1 coulomb has the potential to convert that 12 joules of energy from electrical potential, because it's right next to the positive charge of the positive probe of the electric source, power supply or battery or whatever. It's got 12 joules of potential energy that could actually take off and convert that into kinetic energy, 1/2 mv squared. And if you knew the mass of the charge that was 1 coulomb, you could tell how fast it would go. That's really what the voltage is. So a lot of people will take electric circuits and think of them as like a battery, the low, the negative, the little short bar. That's a wire coming to it, because it's basically assuming the resistance of the wire is so small compared to everything else that wires are perfectly level. They don't change the potential energy at all. But you take a perfectly level wire, it runs into the short end of the battery, which is the negative side or ground. And then the battery goes up, 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 up. And here's the long end of the battery, really, really high. So you can see basically a change in potential energy from going from the ground to the high voltage, which might be 6 volts, 12 volts, 3 volts, whatever, right? And then the wire will leave that and go around in 3 dimensions now, perfectly horizontal, and it'll go out to a load, which will represent as a resistor. And their sign for a resistor is just a wiggle of wire like that. But in 3 dimensions, you'd picture that load as going down back to the original height of the ground, and then a horizontal wire will run from the end of that resistor back to the negative side of the battery again. And that's a nice way to picture electricity because it's accurate. So think of voltage like the potential energy. And then you say, well, what is the stuff that's sort of moving through that? Well, you can think of that as like water. And obviously, if you take a mill that lifts water up from 0 meters to 12 meters, just like 0 volts to 12 volts, then the water will stay level at that point until it goes down, and then it's down at that lower level. Well, that's exactly what it's doing. The water is flowing downward, just like the charges are flowing downward to a voltage they like better. So you might want to know, what is that flow? Well, that flow is the number of charges per second that's going by, and that's what we call current. Okay. And that's measured in coulombs per second, which we define to be the ampere. So now let me make all this into some math, and we can show some neat stuff. So I'm gonna turn on my document cam. And what I was just showing you, for instance, was the idea of a circuit being, normally you would write, say, here's the battery. See how I've got a short line and a long line? That means this side's positive, that side's negative. You can also have it written double like that. And I've even seen it written 3 times before, but generally speaking, I never do it but once or twice. So you can picture that as a circuit symbol for a battery. Now the wire comes out of the battery and goes up to the load, and the load is normally pictured as like that. That's a symbol for a resistor. And then you go back here like that. Now, well, that's the circuit I was just talking about. Basically, all the voltage is going to be applied across the load, because in reality, what's really going on, the wire has a little bit of resistance. So if this, for instance, is 12 volts, okay, so what I'm imagining is I took the voltmeter and I got it set to volts, and I got the red one, the red terminal, plugged into there, to that spot right there. And then the black plugged into there. Then what would be red there is 12 volts. If I keep the black there, then I can just write these bubbles everywhere I want to. Now, in reality, by the time you get over to here, the voltage might actually drop to 11.999 volts, because the battery, the wire actually has some resistance. But if you're only reading to 1 decimal place, you wouldn't even notice that. So you'd still call it 12. And then in reality, once you get to the other side here, you've still got to have charges willing to move from here to here. So the voltage here might be 0.0001 volts right there. And then, of course, the voltage here would be 0 volts. Okay. So that's really what happens. This positive potential is compelling pretend positive charges to run around here. They've lost a little bit of potential energy by the time they got here, but we usually can't even measure it. So we pretend the wires have 0 resistance, in which case you'd call this 12. And you'd call this approximately 0. And you could even say 0.00 probably. Something like that. Okay. So as I was talking to you a second ago, if you want to think about this in 3 dimensions, that's a nice way to do it. Then you have your battery would look something like this. Now this is going off horizontal from here. Notice I've stepped up. I'm going back in space. I'm going over to here. This, on the other hand, is going back here. It's going to go here. So my resistor does this. Like that. So that's a step down. So you can see basically all this is one level. It's technically 0.0001 centimeters high, but it's actually 0 here. So you might as well just say this is level and this is on a different level. And in fact, this level up here is 12 volts and 12 volts. And this level down here is 0 volts and 0 volts. Okay. So as I said, the current is the number of charges that pass, say, a particular point, that point right there, in a time t. And on average, that's delta Q over delta t. But really, you can imagine it's actually going to be dq over dt. And that has units of coulombs per second, which means 1 amp is defined to be 1 coulomb per second. And remember, a coulomb's a big unit, so an amp's a big unit too. And in fact, in terms of danger, it takes a milliamp appropriately applied to a human to kill them. So 1,000th of an amp is enough to kill a human if it's appropriately applied. That's why I'm saying 1 amp is a big deal. Car batteries, for instance, go 200 or 300 amps, at least 100 amps on almost every car. If you talk about Mack trucks and big engines like that, sometimes they'll put out, 1,000 amps or 700 amps, something like that. So this is in fact current, and it turns out that there's something called Ohm's law, and we've studied that already. And it basically says, well, it's two ways to interpret it. V equals I times R is Ohm's law. Okay. Now it was actually, Maxwell showed that Cavendish actually discovered this well before Ohm did, but he did it in a really odd way. Basically, what he discovered is that when he used his body parts basically to connect a circuit, as he increased the voltage, the pain in his arm got higher and higher and higher. So it was getting closer and closer to his heart, basically, and he could feel that pain. And what he noticed is that as this increased, that pain increased, and he recognized that pain was the amount of charges flowing into him. So he actually determined that voltage is proportional to current. And then later, of course, we said, we're going to call that quantity that relates to them the resistance. So that's one way of interpreting it. Whatever you get when you divide the voltage by the current is something that we call a measure of resistance. So that's one way of interpreting it. The other way of interpreting it is that anything has a voltage change across it if a current I goes through it and it has a resistance R. So that's another way of looking at it. And in that case, they're talking about the resistance being an ohmic device. And when they say ohmic device, they mean this R is a constant over the range of temperatures and currents that you're dealing with. So remember, the volt is 1 joule per coulomb. So the units for V is the 1 volt, which equals 1 joule per coulomb. The current, we said, is a coulomb per second. So you'd see that the unit for R turns out to be the unit of V over the unit of I, which again, this was joules per coulomb over coulombs per second. And when you multiply those two, of course, you're dividing by a fraction. That means you flip it over. So that's a joule second per coulomb squared, which we defined as the ohm. Okay. So a joule second per coulomb squared is an ohm. And basically that's just our unit of resistance. Typical resistances are 1 ohm, 100 ohm, 10K, a mega ohm, stuff like that. When we look at Ohm's law this way as talking about ohmic devices, then you can plot I and V and take data for it, which you did in your lab, of course, and you get a straight line, and that R is the slope. Okay. That's an ohmic device. That's why I'm talking about the two aspects. If you plot voltage versus current for like a light bulb, which you guys weren't able to see necessarily with your lab because there's a setting that allowed you to defeat it. But generally speaking, when you did this, what you'd find out is that the light bulb got more and more resistant as you put more and more current through it. And in fact, at some point, the light bulb would light up. That's when the temperature got high enough, and you'd actually see it in the red. And if you kept going, it would go to the white. But this is a non-ohmic device, and it's a light bulb. So the other way we interpret Ohm's law is that at each point there's a tangent line, and the slope of that tangent line is the resistance of that at that point. So there's another resistance, and there's another resistance, so on and so forth. So that's the ways we can interpret Ohm's law. There's really simple expressions. These equations, using this equation is so remedial. I'm not going to take much time to show you an example of that or an example of that, just because it's, you know, trivial applications. So these two equations are super, super important, but they're so simple, it's easy to do. In fact, we give this equation in our conceptual physics classes. And I even, when you give it to a conceptual physics class or a conceptual chemistry class or whatever, you draw it like a circle, and you just do V and I and R. If you want to solve for the current, you cover it up. Oh, I divide the velocity by the voltage by the resistance. If you want to solve for the resistance, oh, I divide the voltage by the current. If you want to solve the voltage for the voltage, you multiply current times resistance. So neat stuff like that. That's why I'm really not too worried about showing you the simple little examples like that. I will tell you that if you look on page 657, you'll see resistor codes. Everybody should know they exist, and that's part of the bummer that we're not getting very much out of this lab is normally holding a resistor, seeing a resistor, which your book has plenty of pictures of them. You actually can read the little codes, and then their codes tell you how big the resistance is and how accurately that number has been measured, okay, or how precisely, if you will. So you can see there's one color band. Resistor might look like this, say. And there's one color band, and then another color band, and then another color band, and then another color band. And this one's the tolerance, tells you how precisely you can expect this thing to be. These are the what we call the number. So it's the mantissa of the number in scientific notation. So for instance, when you say 3.57 times 10 to the third, that's the mantissa. Okay. And then this is the multiplier. So if you see, for instance, a black multiplier means the multiplier is 1. So if you had 28 here, if this were 2 and this were 8, and this were, which by the way, a 2 is red, an 8 is white. So red, white. And then the multiplier was black. Then that would mean this is 28 ohms. And then if this thing was this last one, this tolerance number, if that was gold, then that would imply 5%, or excuse me. Yeah, that would imply 5%. So what I mean by that is 5% of 28 is basically 5 over 10. So you take 2.8 and it's actually 5 over 100, excuse me. You take 2.8 divided by 100, that'd be 0.28, multiply that by 5, that's going to give you 1.4. So you can expect this to be 28.0 plus 1.4 or 28.0 minus 1.4. So that's the range. That's what that multiplier means. Does that make sense to everyone? And normally this color down here is a color that can't be in the first digit. So that's how you find out, because it's actually kind of hard. And sometimes they have none of them. If they don't have one, then that's understood to be 20%. So that's just some of the basics of resistance and resistors and how they work. I will tell you that it should make perfect sense to you that if you imagine a piece of wire, so let's imagine a wire. That wire has a cross-sectional area, A, and a length, L. If you want to calculate the resistance of such a thing, what would you guess? Do you think the resistance would be larger for a longer wire? Imagine this, you're trying to force little charges to go through there. And you sort of think of the resistance as how many charges it stops per second, right? So do you think a longer wire would make more stops than a shorter wire?
Yes.
Yes, because it would take longer for the electron to get through
I
it.
see
So
a
if it was
yes, but that was
shorter,
from
you could do it
11:07
very
this
quick.
morning. So what do you think? Resistance is proportional to the length, or resistance is inversely proportional to the length? What do y'all think?
Proportional.
I'd sometimes tell people, imagine going to I used to be a punker in high school. So there were these things called slam dances. And if you imagine trying to walk to it through a hallway that there's a slam dance in, right? Would it take you more time to get through a very long hallway or a very short hallway?
Professor, do you hear us?
Professor?
It'd take a longer
Professor.
time to get through a very long hallway. Therefore, the resistance of you getting through there is increased by L increasing. So you'd say R is proportional to L. Now, if this opening were just the surface area, oh, y'all are speaking. Okay, gotcha. So y'all are speaking now. I can hear you, but you can't hear me. I mean, I can't hear you. Sorry, that stinks. Okay, no problem. So yeah, that makes the interactive class experience a little less interactive, doesn't it? So anyways, so now let's imagine that this doorway is just the size of a human body compared to, say, a big hallway, which is like 20 foot wide by 10 foot tall. Now, do you think the smaller doorway allows you to get through the slam dance quicker, or the bigger doorway? So obviously, since I can't hear you, I'm waiting for people. Yeah, the bigger one's better. So what that tells you is the bigger the area, the less the resistance. Does that make sense? So if I make the doorway easier, the easier it is to get through, and easier is the opposite of resistance. So I'll put it A like that. Well, that turns out to be exactly the right expression. Now all you got to do is account for the slam dance, right? Is it a geriatric group doing slam dancing? Because, all of us that used to slam dance are now old, right? So some materials are really compelled to not move very fast, and other ones are compelled to move very fast. So you've got to take into account the material. So it turns out the resistance is equal to some constant. That constant is due to the particular material times L over A. So that's a material property. Just like density is a material property, rho, the resistivity is a property of the material, and its units for resistivity. You can see here, this has got to be ohms. This is going to be like meters over square meters. So this should be a ohm meter. And that's what the resistivity is. Your book gives you a table of resistivities, and you can see that they run basically around 10 to the negative 8. When you get to carbon, you get 10 to the negative 5th. That shows carbon's a bit of a conductor. It's a semiconductor. And then insulators go like 10 to the positive 9 or 10 to the 12. So conductors on the order of 10 to the negative 8. Semiconductors, they're on the order of 10 to the negative 5. Even one silicon, for instance, has a resistivity of 0.1. And then insulators on the order of 10 to the 9th to 10 to the 15th. Okay. So that's the resistivity. And this, I mean, I suspect you can imagine exactly how to solve a problem like this. If someone tells you, hey, I need a wire to only be, 4 ohms of resistance, we're using copper, then you can look up rho for copper, and you have to tell them what radius the wire should be, and then by calculating what is A. Okay, so that's a very simple, straightforward example. And you can see an example like it where they do it for speaker wires in example 25.5. Again, this stuff is a little too remedial, elementary, if you will, to waste much time on examples. I want to make sure I get through the big concepts and the big equations, so we know the ones that are important. So I found another equation that's valuable, and that's resistance is equal to rho times L over A. Now, the other big thing we're going to need to know is, I've hinted to it a couple of times. I've said, for instance, that the battery's resistance actually increased as the temperature went up. So you might ask yourself, well, how does resistance depend on temperature? Well, it depends on temperature like almost everything does. Oh, one thing I should mention, by the way. There's something called the conductivity. And the conductivity is 1 over rho. So you might see that word come up on occasion. I just wanted to make you aware of that. Conductivity is 1 over rho, and it has units of reciprocal ohm meters. So the unit of ohm, the conductivity is 1 over ohm meters, or ohm meters to the -1. Okay, so just so you know, that's a thing that we use as well. So if they ask you to solve for conductivity, you're going to solve for the resistivity and then take the reciprocal of it. All right. So I just want to make sure I mention that, just because that's some, sort of housekeeping type stuff. Now, if you want to see what the temperature dependence is on resistance or resistivity, you can say, well, it turns out that I suspect the change in resistance to be basically proportional to temperature. So I would expect rho minus, let's say rho at a temperature T minus rho at some initial temperature T0. I expect that to be proportional to the change in temperature. Okay, so that looks like a linear response. And in fact, what we use is something called the temperature coefficient of resistivity. So we'd say rho T minus rho 0 is equal to some alpha times T minus T0. And this is called the temperature coefficient. Of, not or, sorry about that, resistivity. Okay, now that works fine, but they normally express it this way. They'll say rho T is equal to rho 0 times 1 plus alpha T minus T0. When you look at it that way, you see that the alpha must have units of 1 over Celsius degrees. Okay, when you put the degree after, that means a difference in temperatures. When you put the degree before, that just means a temperature. So 1 over the Celsius temperature. You can see that that has to work out that way, because these have to have the same unit, and this has to be able to be added to a pure number 1. But you should recognize that when I pull this over here, then I'm just going to have a rho 0, and I factor that out, and basically that's how that equation comes to be. Okay. So this is the one we normally use. This was just the argument for it. So you can solve all sorts of neat problems with this. And for instance, you can use that to define a thermometer. In fact, thermistor is one of the words you use. And for instance, if your dryer stops working or stops getting hot, sometimes it's one of your thermistors. And a thermistor is basically something that has a known material, material whose resistivity, temperature coefficients of resistivity, you know, and then you put it in there, and basically what happens is the current changes as the temperature changes, and therefore that they can use that change in current to dictate how high or determine how high the temperature is, say in the dryer or something like that. So when you do that, then you can actually use the same equation to find out temperatures, and you keep a house from burning down or stuff like that. So that's some of the cool sort of things you can do with that. But that is how resistivity is related to temperature. You can also, of course, write R is equal to R0 times 1 plus alpha T minus T0, and it's still the same constant alpha, because really all you're doing is multiplying by L over A and L over A, and you'll end up getting, remember, R is equal to rho L over A. So that's the exact same equation. So you just keep that in mind. If they give you resistivities, you want to use this one. If they give you resistances, you want to use that one. Now we're going to get into the little bit bigger part and the more important part. I've done some simple things showing you how current is defined and stuff like that. Now I want to talk about power. And remember, power is dW over dt. That's how we defined it in the first semester of this course. And in this case, what we're going to do is say power is actually equal to the change in potential energy per unit time. Because remember, the work you do on something is equal to the change in potential energy as well. So that works out just fine. Well, if you remember, we found that U is equal to Q times V, right? So what that means is when I take d by dt of Q times V for a given voltage, I get dQ over dt times V, which is IV. dQ dt being current, right? So that's one big important expression, P equals IV. And this works for AC too. There's as long as whatever you're using are the same, it'll work out fine. So for instance, if you know your AC amps and you know your AC voltage, you multiply those two and that'll give you the power. And more importantly, if you find out the power that an object is using, let's say a compressor or a welder or something like that, it'll have a power reading in watts. And you know that house voltage is like 125. And for safety, you might even want to call it 115, because you're going to take the P and divide it by the voltage, and that'll give you how much current it draws. And then you got to make sure any kind of wire you're using can handle that much current. So for instance, I have an edger that I use. It's a Craftsman. I used to use, my yard's too big, but I went and bought a 75-foot extension cord to run it out there. But the one thing I had to check is what was the power of that device. And luckily I did that, because most of the 75-foot extension cords couldn't carry enough amperage. And when you do that, you could literally be sitting there holding the wire in your hand while you're running the edger and have it melt right through the housing and burn the crap out of your fingers. I've actually had that happen before. So that's a really good thing about this formula, is in everyday life, you can use that to determine the current that something draws. And that will give you an idea of what kind of extension cord you can or cannot use. One of the first things I noticed recently, I bought a new compressor and called Home Depot because one of the tools that came with it was broken. And the hotline said, if you're calling about a compressor, first make sure you're not using an extension cord. The reason being is that compressor's high power, and it's very rare that you have an extension cord large enough to handle that kind of current. So it is a big deal. Now, if you don't know I and V, what about if you just knew, say, I and R? Well, you can now use V equals IR to remove the voltage. So if you just knew I and R, I could put I squared R there, because I'm just replacing V with IR. So that's another expression that's kind of helpful. And this one's actually the reason that we carry really high voltage wires out through the country. So those really high ones that are on those big towers, they're not 120 volts. They're usually 200,000, 500,000, even 1,000,000 volts in some cases. Often people work on them by being delivered there by a helicopter. If you want to see some neat stuff with that, go to TikTok and look for, I think it's Grandy 210 or something like that. This is a guy that teaches people how to deal with those wires. He's called a hot stick operator. But anyways, you can see cool videos of that high voltage and some of the stuff it does. It's really cool. Now, another option is, what if I don't know R? What if I don't know I? Okay. If I don't know I, then I is equal to V over R. So I could also say V squared, because this will be V over R over R. So that's another expression for power. Okay. But it turns out there's a equation, and we don't learn it in this chapter. We learn it in a later chapter, but there's a transformer equation that basically says Vn is equal to the number of turns going in divided by the number of turns going out times V out. So what happens is, if you increase, if you take a wire and run it like that around an iron core, like a Pilgrim's belt buckle that you remember from grade school in the plays and stuff, and then you have another number of turns on this side going out, and this side is, say, 10,000 turns, and this side is 100 turns, then if the voltage going in was equal to, let's say, 120, then the voltage coming out will be 120,000. So they build something like this called a transformer that takes that 120 voltage and creates 120,000 volts. But at the same time, the equation IN is equal to N out over N in times I out, means that the amps actually drop by the same factor. A house, for instance, uses 200 amp service generally. So if you're feeding 10,000 houses, you'd need 200 amps per house times 10,000 houses. Okay, that's 10,000 times 200, so that gives you 2 million amps. Okay, so if 2 million amps went in, then now it's dropping to 20,000 amps out. That same transformer. Because this current went down by a factor of 100, you're losing a factor of 10,000 less power, because basically just running current through a wire, that resistance is going to cause a heat loss going to the environment. And the power company realizes that, and they can save a buttload of money by upping the voltage and decreasing the amperage by, it's usually more than a factor of 100, but I just did a factor of 100 here. And you can see that this I squared R drops the power by a factor of 10,000. And that's just pure wasted energy that they're reducing. So that's better on our pocketbook. Now you might say, well, wait a second, the voltage is squared too. Well, that's accurate, but remember, what's fixed here is the resistance. Okay, the resistance is rho L over A, and the L you can't do anything about, right? Because it's got to go a certain distance to get to that city. The rho you can change a bit, because you could use copper versus aluminum versus steel, and the area you can change a bit, but you can't change the amount of current that you're going to go through, because you have to serve them about 200 amps per house. So that's why this equation is the valid one, not that one. I mean, they're all valid, of course. It's just what you're talking about here is V, is how much the voltage drops between the 120,000 at the pole to the other end of the neighborhood. So you're going from the power company at at 12,000 volts, and you're going to get to the house at something less than 12,000 volts. That's the V that goes there. That's not helpful at all, right? Okay. So that's some of the stuff about power. Your book asks some really good questions about hooking headlights up parallel and stuff like that. Those are kind of fun questions that we'll do. I think that's actually in the next chapter, to be honest with you. Yeah, it is. It's in the next chapter. And it does calculations like, will the actual fuse blow and that sort of stuff. Those are all really good questions. But the main thing I wanted you to get through here is to get through all these major topics. Which is power, voltage, Ohm's law, resistance, current, all those things, how they're related. So I'm doing sort of the lecture material, the concepts and stuff, and then next time we'll work examples. That way I can be assured that you can have your homework done by Wednesday. Okay, the concepts are due Sunday. The conceptual homework's due Sunday. The problem homeworks are due by Wednesday. You can probably do, I would bet, the whole homework set after I'm finished with this. Okay. We started at what, 11? So we're supposed to go to 12, 15. No, we started at, we started 11. We're going 12, 15. So I got about 15 more minutes. What I will tell you about AC is basically AC is really good because we can use transformers quite easily with them. And it's really good because it actually is the way power is created. So most modern power plants use something to create steam, and then that steam drives an impeller, and that impeller generates electricity. The way they do it is basically, you can imagine an impeller, which is like a prop on an airplane or something like that, and you force steam through it, and that steam can be gotten, for instance, from cooling down nuclear energy. So you can produce a buttload of heat in a nuclear reactor. That nuclear reactor can cause water to boil, and then that steam can be flushed through here. And what you're going to have is a series of magnets, north, south, north, south, north, south, like this, magnets all attached to this shaft of the prop. In principle, all you have to do is have a loop of wire around that, and automatically you're going to generate electricity or a current that looks like this. We're going to learn that later when we start to cover first Ampere's law and then Faraday's law, which is the more important one. Faraday's law is what tells you this happens. So when you actually make a power source, it automatically comes out this way. And Tesla's the one that gave us the 60 hertz, for instance, because he found that was a good, easy electricity to produce. And what we have here is V peak. And that's 1 voltage, but that's not the 125 volts that we're talking about. Okay. It turns out if you take the integral of V squared dt over a whole period 0 to t, that, and then take the square root of that, that gives you VRMS. And that is about here. And that's VRMS. That's what we actually say when we talk about 125 volts. Okay, so you take it over a whole cycle, that would be basically from here to here is 1 period. And that's what you read when you read just on an analog meter or a digital meter. You read the voltage of an AC source, you're reading that VRMS. Now the equation P equals IV, what is that using? Well, that's sort of the point. If you take the IRMS and the VRMS, it turns out that VRMS is just equal to V peak over the square root of 2. And IRMS is the same thing, because there's a graph like this for, instead of voltage per time, there's a graph like this for current per time, and that's I peak over the square root of 2. So it really doesn't matter too much what you use. You could in principle use the peak values or the root mean square values, but the main thing is P on average will be equal to IRMS times VRMS. If you wanted to actually use the peak values, then what you're going to see is going to happen is I times V, that's going to be 1/2 like that, because the square root of 2 comes from each of them. That makes sense. And you can see other expressions like 1/2 I0 squared R, or they're saying 0. I was calling it peak, so I'll stick the P on there. Are 1/2 V peak squared over R. So all of these are actually valid for R, for AC. And AC, remember, means alternating current. And really what it's doing is alternating in direction. So what that means is this from here to here takes 1/60th of a second here in America. They use a different frequency in Great Britain and other countries. That's why one of the reasons you have to get basically you have to get a device that converts the current and voltage to what we use here in America. They also use a higher voltage peak to peak as well. But either way, what's going to happen is it's going to be 0 for a split second, the voltage will be. And then for about 1/100th of a 1/120th of a second, it's going to be a positive voltage, meaning it's going to be going, say, around clockwise, and then it reaches 0 again. And then the next 1/120th of a second, it's going to be going counterclockwise, and then another one clockwise and another one counterclockwise. That's what alternating current means. It's alternating its direction in time. Now, finally, I'm going to introduce a quantity, and this will be the last topic. Again, I'm just covering the topics right now. I'll solve some problems in the next meeting, and we'll be done with chapter 5. The quantity I'm going to describe is called the current density. And that's going to come in handy when we do the Biot-Savart law and as well as the Ampere's law. So the current density is called J and is actually a vector. Its units are amps per square meter. So really what it comes from is I is equal to J dot dA. So it's an integral over a surface area A of a wire. So basically it's the current density, it's the number of coulombs per second that go through each little square centimeter, say, right? Well, that's what that is. Now that we have that, we can try to figure out on a microscopic level what exactly is current. So this is our microscopic understanding. So if you want to calculate the current, you got to realize, okay, well, current is delta Q over delta T, and we let the delta T get really, really small. So we might say, well, wait a second, the amount of current that's moving, or excuse me, the amount of charges that are moving is really going to be the number of charge carriers, which is basically the electrons, number of E minuses, times the actual charge per particle, which is negative E. Because the electron has a charge E, a negative E, which equals 1.602 times 10 to the negative 19th coulombs, right? Now, it turns out that this N total number of charges can be equal to the charge per unit volume times the volume. And I'm going to put the V like this so we won't mistake it for voltage. So it's N times V times, and I'll put a negative in front, times E. And now I've got the actual charge that you know, might pass a particular point in the wire at any time. So we might be looking, say, at this point. Okay. Now, you might want to say, well, what exactly is that volume? Well, that volume is going to be the cross-sectional area times this length, which would be the drift velocity times the time taken, delta t. Okay. So you can see that delta Q is now going to be equal to negative N E. Now, in place of V, I'm going to put the area, A, times V, drift velocity, delta T. So what I'm saying is, because an electric field is going to be established in this wire that I told you is like a waveguide, that's going to compel the electrons to drift a little bit. They're going to still be colliding a lot, but overall, they're sort of making their way in the opposite direction of the electric field. And their velocity will be some velocity that I call V sub D, which means the drift velocity. Okay. So that tells me that the current, which is delta Q over delta T, is just equal to negative NEA times the drift velocity. So now I've got it all in terms of vector symbols, but that's also equal to J is actually equal to the current divided by A. And I've got a current in vector form now. So I can see that J, the current density, should equal negative NE times V sub D. And that is the microscopic description of current. Now, this is one that's a little more complicated. It's more like a chemistry problem. In fact, you know how you used to have to convert things to moles and all that weird stuff. But you might imagine, for instance, a particular wire, and you might want to calculate what the drift velocity is, and you might want to calculate, for instance, what the current is, that sort of thing. So let's say we have a copper wire. So this is, what time is it? Only got 3 minutes. It'll be quick. So this is an example. Copper wire. That means 1 electron per atom. That's most conductors have 1 electron per atom that's free. Some of them have more, but copper is one of the ones that has 1. We're going to say its diameter is equal to, let's say, 4.00 millimeters. Okay. And I'm going to say it's carrying a current of I equal to 10.0 amps. Try to keep everything in 3 sig figs. And I'm going to say it's at 20 degrees Celsius. So T is on the order of 20 degrees 0.0 Celsius. Okay. And what I'd like to calculate is what is the drift velocity and J. Okay. Well, the J part's straightforward. I just have to say J is equal to I divided by A. And of course, I is equal to 10.0 amps. The A is pi d squared over 4. Right? So that's 10.0 amps over pi times, I said 4 millimeters. So 4 times 10 to the negative 3rd meters squared. And I'll put the 4 up here. So I can get, if I find my calculator, oh, there it is. I can get 4 times 10 is 40. I'm going to divide that by parentheses 3.14159 times 4e to the negative 3, and then I'll square all that, or just that 4 times 10 to the negative 3rd, and I get 0.79577 with 2 extra digits amps per square meter. Okay, that's the easy part, but it was one of the things I was asked for. Now the other part is getting VD. Well, to get VD, we need the N, and of course we got the electron charge. Well, the N is equal to basically the total number of particles in a given volume V. Well, that might seem virtually impossible, but if we consider 1 mole, then we get a pretty neat explanation. We can say N is equal to the number in 1 mole, which everybody knows what that number is, divided by the volume of 1 mole. But again, that part's not very easy, but we know this one's Avogadro's number. And then all we need to do is, since density is equal to mass over volume, we can see that volume is equal to mass over density. So I just put in the molecular weight divided by the density of copper. Okay, that's the key point. That's the whole reason I'm showing you this. Now you've got Avogadro's number, you got the molecular weight you get from the periodic table, and you can look up the density from the internet, or probably in chapter, I think 2 or 1, it might have been in there as well. So we ultimately got that in. This is for one E minus per atom. If you had a particular conductor that had 2 electrons per atom, then you have to multiply this by 2 or 3 or whatever. So in this case, it's going to be Avogadro's number times the density of the metal divided by the molecular weight of copper. And that gets us it. And of course, now you're in a position where you can calculate that the D is actually equal to getting rid of the sign. It's going to be J over N times E. So that's it. Okay, I won't even finish the numbers because the time's up for the class. But you can, I'll probably do them on the notes and leave them there. But you guys are free to go. Let me know if you have any questions. I will be around.
Thank you, Professor.
See you this afternoon.
Have a great day, Professor.
I hope I got Christian and everybody's message. Summer, did you have a question? You can type it, please, because evidently our hearing's not working. Nope, guess not. All right, so I'll take this. Now I'm going to divide it by the N. Or actually, I'm calculating the N right now. And then I'm going to divide that by the molecular weight of copper, which is 63.5 times 10 to the -3 kilograms. Remember, the molecular weight is grams per mole. That's another way of writing it. So you have to put the 10 to the -3 there to make sure you get that right. And then that'll cancel out with the kilograms up there. And I get basically electrons per cubic meter per mole. And this is kilograms per mole. So that mole cancels out, that per mole cancels out. So we just get electrons is the final answer, the final unit anyways. So when I do that, I do 6.02 e to the 23 times 8.9 e to the 3rd. And I divide that by 63.5 e to the -3rd. And I get 84.375. I'll just leave it at 37. That's 1 extra sig fig. 37 times 10 to the 27th electrons. Okay. So now the drift velocity is just in magnitude. It's just going to be J, which we calculated 0.79577 extra sig figs there, amps per square meter, divided by, oh, and this is actually electrons per cubic meter. Sorry about that. That's why I wrote those units up there to keep from making that very mistake. So anyways, I'm going to divide this by 84.37 times 10 to the 27th E minuses per cubic meter. So you can see the cubic meter on the top will come to the top and cancel out with the meter squared in the bottom, and I'll get coulombs per second times meters. I still haven't put in my electron charge, so I got to put that in as well. Sorry about the equals. So that's 1.602 times 10 to the negative 19th coulombs per electron. So now you can see the electron cancels out in the units, and now I've got coulomb meters per second over coulombs. So that just gives me meters per second, which is exactly what I expect. So that's 0.79577 divided by 8.43 times 10 to the 8.437 times 10 to the 28th times 1.602 e to the negative 19th. And that gives me ultimately, I did not expect that number to be that small. Something seems to have happened, but all my numbers look right. 10 to 28th. 10 to the 28th. I did 10 to the negative 19th. I am getting 58.87 times 10 to the negative 12th meters per second. That's a lot slower than I expected. I'm trying to figure out why. I'm thinking it might be in my amperage. I did 10 amps divided by pi d squared over 4. That's the same thing as pi r squared. Let's check that again. So 44 times 10 divided by parentheses 3.14159 times 4 exponent negative 3, and that quantity is squared. That was 10 to the third. No wonder. So I'm off by a factor of 1,000,000. That makes more sense. This was actually supposed to be, write it with a different color marker so everybody will know it. I just misread it. It's 795.8 times 10 to the third amps per square meter. I should have looked closer at that. That's going to make this be off by a factor of 1,000,000. So I have to take times 10 to the 6 to correct that. And that'll make this 10 to the negative 6 meters per second, which is much more reasonable. Okay, so ultimately it gets 58.87, one extra digit times 10 to the negative 6 meters per second for the drift velocity. In your book takes the time to use a formula we learned from thermodynamics to show that the drift, the actual random motion of the atoms and, or excuse me, of electrons in something that's 20 degrees Celsius is 1.2 times 10 to the 5th meters per second. So this is markedly smaller. VRMS is actually supposed to be square root of 3 kT over m. And then you do that for electron, you get 1.2 times 10 to the 5th meters per second at 20 degrees Celsius. So you can see this drift velocity is still really, really small. It wasn't as small as my errant calculation, but it was still really, really small. It goes about 58 microns every second. Whereas the electrons, just being at 20 degrees Celsius, they're going to be bouncing around at 1.2 times 10 to the 5th. So it really is like the electrons are just sort of drifting along very, very slowly. And the fact that it's slow at all is what normally strikes students as odd. And that was the whole reason why I wanted to do a calculation and get an actual result for you. So that's it. Have a good day.